Let's talk about logarithmic differentiation. The standard derivative rules can be difficult or impossible to apply to some functions. For example, y equals the square root of 2x plus 3 over sine cubed x times the quantity x squared plus 4 to the fourth. Well, it's possible to do this derivative, but it's pretty difficult with all of the quotient, product, and chain rules involved. And something like y equals x to the square root of x is actually impossible to do with the standard derivative rules. Logarithmic differentiation gives us a nice way to handle these by first applying logarithms, which allows us to use properties of logs and then use implicit differentiation. As a reminder, here are some properties of specifically the natural log, which is the one we'll use during this process. So natural log of x times y is natural log x plus natural log y. Natural log of x divided by y is natural log of the numerator minus natural log of the denominator. Natural log of x to the a is equal to a times natural log of x, and then natural log of e to the x is just x. Here are the steps we're going to apply for logarithmic differentiation. We have to start with y equals some f of x, and then take the natural log of both sides, so natural log of y equals natural log of f of x. And that's when we're going to simplify the right-hand side using log properties. And we'll differentiate implicitly with respect to x, solve for y prime or dy dx, and then replace our y with the original function. Here we want to find dy dx using logarithmic differentiation, given y equals cosine x times e to the x times the quantity x cubed plus 1 to the fourth. So we'll start by taking the natural log of both sides, and now on the right-hand side, we'll apply log properties. We have natural log of, inside here, we have the product of a couple functions, so we're going to split this up. We're going to have natural log of cosine x plus natural log of e to the x plus natural log of x cubed plus 1 all to the fourth. Now, there's a few things we can do here. The middle term, natural log of e to the x, is going to simplify to just x. And then for the last piece, I can also apply the log property where the 4, because it's in the exponent, can be brought to the front of the log. So now that's 4 times natural log of the quantity x cubed plus 1. And there's nothing else I can do here. I cannot split up the log of a sum or difference, just a product or quotient. And now we apply implicit differentiation. We take the derivative with respect to x of both sides. So I've written that operator here, d dx, in front of both sides. On the left side, we have the derivative with respect to x of natural log y. So the derivative of natural log y is 1 over y, but the derivative of the inside y is dy dx. There's that implicit differentiation. Now, on the right-hand side, we can differentiate each term. That was the idea of using the log properties. And so the derivative of natural log of cosine x, we're going to put the inside in the denominator. So we're going to have cosine x, and then its derivative goes in the numerator from the chain rule. So we'll have negative sine x, and then the derivative of x, that's just 1. And then plus, over here, I'm going to leave that 4 in front, and then the derivative of natural log of x cubed plus 1, again, the inside goes in the denominator, so x cubed plus 1, and then its derivative, 3x squared, from the chain rule, goes in the numerator. All right, so let's clean this up a little bit. We have sine over cosine is tangent, and multiplying the 4 times the 3, we have 12x squared over x cubed plus 1. And so we're trying to solve for dy dx. So I'm going to have to multiply both sides by this y here, the reciprocal of 1 over y. So here, the y times 1 over y cancels, and I end up with just dy dx is equal to negative tangent x plus 1 plus 12x squared over x cubed plus 1 times y. But let's remember, from the original equation, y was equal to this function of x up here. So I'm going to go ahead and replace this y with cosine x times e to the x times x cubed plus 1 to the fourth. So now I have dy dx completely as a function of x instead of leaving the y here so that it's a function of x and y. All right, let's do another one. Find dy dx using logarithmic differentiation. We'll start by taking the natural log of both sides. And now, on the right side, we're going to use the log property that I can take this exponent and bring it to the front of the log. So I have natural log y equals the square root of x times natural log x. And then we're going to take the derivative with respect to x of both sides. And on the right-hand side, I'm going to have to use a product rule. All right, on the left-hand side, the derivative of natural log y with respect to x is 1 over y dy dx, and that's going to be consistent throughout all of these problems. The right-hand side, again, needs a product rule. So we're going to go ahead and leave the first function alone. The derivative of natural log x is 1 over x, plus we'll leave the second function alone, natural log x, times the derivative of the square root of x. So that's one that you want to get pretty quick with, where you just know the derivative is 1 over 2 times the square root of x. So now we have 1 over y dy dx is equal to, if I simplify, this is 1 over rad x plus natural log x over 2 rad x. I can make them have common denominators, so we'll make that a 2 and that a 2. And so we'll go ahead and multiply both sides by y. So we have dy dx is equal to 2 plus natural log x in the numerator, and then over 2 times the square root of x in the denominator times y. So now the final answer is going to be just replacing y with x times radical x so that I end up with a function of x. So 2 natural log x over 2 times the square root of x times x to the square root of x. So this is my derivative. All right, let's go ahead and use logarithmic differentiation again to find y prime given this function from earlier, y equals the square root of 2x plus 3 over sine cubed x times the quantity x squared plus 4 all to the fourth. So we'll start by taking the natural log of both sides. And in that process, I also rewrote the square root as the power of 1/2 and sine cubed x as sine x all cubed. And then we're going to apply log properties on the right-hand side. So here we're going to have natural log of y equals natural log of the numerator, 2x plus 3 to the 1/2. And then any pieces in the denominator are going to be subtracted, any parts of that product. So minus natural log of sine x all cubed minus natural log of x squared plus 4 all to the fourth. And then we can bring each of those exponents to the front of their own log. And so once we do that, we're set up to take the derivative with respect to x of both sides. Now I did this log property expansion in 2 steps, but ideally you'd want to be able to just go straight to the most expanded version of our original function so that we can just jump straight into differentiation. So here the derivative on the left-hand side is going to be that 1 over y dy dx, and then we can do the derivative of each piece on the right separately. So we're going to have 1/2, and then we'll put the 2x plus 3 in the denominator and its derivative 2 in the numerator, minus 3 times here we'll put the sine x in the denominator and its derivative, cosine x, in the numerator, minus 4 times we'll put x squared plus 4 in the denominator and 2x in the numerator. So we'll go ahead and simplify just a little bit. These 2's here are going to cancel, so just 1 over 2x plus 3. Cosine over sine is cotangent, so minus 3 cotangent x, and then 4 times 2 is 8, so we have 8x over x squared plus 4, and then we'll multiply both sides by y. And then, of course, we're going to have to go back and replace y with the original function of x. And so this is my big final ugly answer. There is some slight simplifying we can do for some of these problems, but honestly, I'm just going to go ahead and leave it here with our answer as a function of x. And now let's differentiate y equals tangent x to the x. So we're going to take the natural log of both sides, and that will allow us to bring the x in the exponent to the front of the log on the right-hand side. So we'll have x times natural log of tangent x. Now we take the derivative with respect to x on both sides. On the left side, we get that 1 over y dy dx. And then on the right-hand side, we need the product rule. So I'm going to leave the first function alone, x. The derivative of natural log tangent x, I'm going to put tangent x on the bottom and its derivative on the top from the chain rule, which is secant squared x, plus, then I'm going to leave the second function alone, which is natural log of tangent x times the derivative of x, which is 1. Okay, so now I'm going to go ahead and multiply both sides by y, and I'll be left with dy dx is equal to x secant squared x over tangent x plus natural log of tangent x times y, which was tangent x all raised to the x. And we want to be careful and include parentheses around tangent x because the entire quantity is raised to the x power, not just to the x. So in summary, when do we need to use logarithmic differentiation? When trying to differentiate y equals a function of x with a function of x in the exponent. Otherwise, it's optional, but can be a time saver if you have a complicated function with many products, quotients, and/or expressions with exponents.